this is an unusual example because normally when you have some kind of 2x to the fourth, 17x cubed, etc., you're going to go for the rational roots theorem. With the synthetic division and the guessing, you're going to make a list of possible roots, and then you're going to check them by synthetic division, see what's an actual root. But in this case, look at what's given to us. Not only do I need to factor this and find roots, all that normal stuff, but I'm given a complex root. It has an imaginary part to it. Now, imaginary numbers, complex numbers, rational roots cannot handle those things. It was not designed for those. So as soon as I see that complex root, I'm thinking, whoa, this is a big warning flag. Do not proceed with rational roots theorem. Instead, let's go with the conjugate root theorem. Okay, and the reason is, what if all the roots were complex or imaginary? Rational roots theorem would never find them. So you'd just be spending hours. It would never get anywhere. Instead, I'm going to use the complex root theorem right here. Okay, so let's keep going and think about what complex conjugate root theorem says. It says complex roots travel in pairs because this is a real polynomial. You have to have two complex roots at a time, and they have to be conjugates of each other. So this one right here on the left, that's our first root. That says there must exist a second root. And here it is, the conjugate of the first one. Okay, so negative 3 minus 2i leads me to negative 3 plus 2i. Now, knowing two roots, I could probably factor this thing down to a quadratic, right? It's a fourth power right now. If I know two roots already, I can bring it down 2 powers to a quadratic. And maybe I won't even need rational roots at all. So let's see, how are we going to use this? Well, there's a theorem called the zero product theorem, which says if you do x minus a root times x minus a root times x minus a root and so on, you see I've got 4 roots here. That's the factored form of your polynomial. We just need to know what those roots are. Now I already have 2 of those roots, right? Given up here in blue, the conjugates. So it doesn't help me figure out what x3 and x4 are yet, although I'll bet I can get closer. Let's write it this way. Look what I've done here. This is x minus x1, x minus x2. Okay, I'm leaving x3 and x4 aside for now. But I'm just going to rearrange the items in blue, and let's see if we can combine those together in a little more useful form. I've taken away the parentheses, I distributed the negative sign, and now I get x plus 3, x plus 3 with a negative or positive 2i. And if you notice, those are conjugates of each other too. The factors have to be conjugates. And if you multiply 2 conjugates together, you know what's going to happen. The imaginary parts disappear. Well, that's really nice. And I'm also going to point out that this is set up right now as a difference of squares. My a term is x plus 3. My b term is 2i. So what I really have is a plus b times a minus b. Okay, well, we can use that. If I multiply difference of squares, a minus b, a plus b together, I get a squared minus b squared. So that's what I've got right here. I took my a squared, that's x plus 3 squared, and then my b squared, which is 2i squared, set up a difference, and now I'm going to expand that out and see what we get. So from the x plus 3 squared, I get x squared plus 6x plus 9. From the minus 2i with the squared on the outside, that becomes 4i squared, that becomes negative 4. The sign reversal makes it a positive 4. Look what we've got here. This is getting closer to something I can really use. And if I simplify it a little more, I get x squared plus 6x plus 13. Okay, that is an irreducible quadratic. That's what we were kind of shooting for here. See right here where it says irreducible quadratic factors? So I've got one of them right now. I just need to figure out what x minus x3 and x minus x4 are. What are those factors? Well, I've mentioned this a bunch of times, and it bears repeating. Factoring is kind of synonymous with division. If you can do polynomial division, you can do factoring. So we need a way to divide the entire polynomial, that 4th degree thing up here. We need a way to divide that by this quadratic. And if I can do that, I'll find the remaining 2 factors. Well, synthetic division is not great at dealing with quadratics. So in this case, I'm actually going to turn to long division. And I pre-wrote this here so I could get through this a little faster, but just a quick review. First step you do is you put your whole polynomial here, and we're going to focus on the leading terms. I do 2x to the 4th divided by x squared. Okay, that division leads me to 2x squared. Okay, now what do I do once I have 2x squared? Well, I just multiply it back down, except this time I multiply it back down times the entire polynomial. So that's going to give me this right here, 2x to the fourth plus 12x cubed plus 26x squared. And if you want, pause the video. By all means, walk through these steps one at a time. The next thing you do is subtract, and you get these two terms. Oops, I'm still on the eraser button. You get these two terms right here, and then you carry down. And then we start over, right? So it becomes 5x cubed divided by x squared. Well, that's just 5x. And then you multiply back down, 5x times this entire thing right here. So it becomes what you see in parentheses, 5x cubed plus 30x squared plus 65x. And then we subtract, and we get this term, plus 2x squared plus 12x plus 26. And you repeat it again, one more time. 2x squared divided by x squared equals 2. And then I'm going to multiply back down again. And look at that, I've got a remainder of 0. Now, I suspected I had a remainder of 0 because I knew at the very start of this that x squared plus 6x plus 13 was a root, or was a factor, an irreducible quadratic factor. So I knew there had to be a remainder of 0. What remained was to figure out this thing. This is my quotient, which means I can write my polynomial in the following form. I can say f of x equals x squared plus 6x plus 13 times 2x squared plus 5x plus 2. Now, if you've made it through this, you probably understand how to factor this one right now. Okay, that's not hard. I've been over that in other videos. I'm just going to put that answer up here. You can double check it. There are all sorts of methods to do this part. You could do the guessing method, you could do the box method, the big X, whatever. The important part is you should know how to factor quadratics by now. And what I have here is now fully factored in terms of linear factors. That's these guys. Those are my linear factors. And my irreducible quadratic right here. Okay, that's what I was going for. So this is your fully factored form. The last question is, well, what are my roots? Okay, so your roots are going to be, let's pick, magenta's going to clash. That would be ugly. We're going to do green again. Here are my roots. From this one, okay, I have, what were these things again? -3, yeah. -3 minus 2i and -3 plus 2i. Okay, those are my two roots there. From this factor, it's -2. From this factor, it is -1/2. Okay, so we've got some real roots, some complex roots. And if you had done remainder theorem from the very start, you would have actually found these two. It probably would have taken a little while because that -1/2 would have taken some guesswork to get to. I think that the complex conjugate theorem was a quicker way to go about this.